Welcome to this Higher Physics video for the R Dynamics universe on impulse, part of the momentum section of the course. So what are we looking at in this video? Well, we're looking at how to apply the law of conservation of momentum, and we're looking at the fact that impulse is equal to the force times the time, understanding what impulse is, of course, and that impulse is equal to the change in momentum, and how to carry out calculations using that. So we might think that momentum and conservation of momentum is quite abstract quantity, but actually if we've been on a plane, which most of us have, or possibly a jet ski, less of us have been on those, both of those things work by the laws of conservation of momentum. Because what a plane is doing to fly forwards is a plane is pushing the air backwards and the air is pushing the plane forwards. And we've got a conservation in momentum of those two things. So there's the momentum of the air backwards and the momentum of the plane forwards. And this is what causes things to move. And the same for a jet ski. Jet ski pushes the water backwards and the water pushes the jet ski and you on the jet ski forwards. So let's have a look at some of the relationships here. So Newton's second law says the unbalanced force is equal to the mass times the acceleration. But we already know that the acceleration is defined as the change in velocity divided by the time, or v take away u, where u is the initial velocity and v is the final velocity divided by the time for that acceleration. So if we combine those two relationships together, we get the one in the middle at the bottom there, that the force is equal to the mass times v minus u over t. If we then multiply out the mass, we get mv minus mu divided by t, and then if we multiply the time by the force, we get mv minus mu, and we should be able to see now that mv minus mu is the same as the change in momentum. So we've got a link between the change in momentum and the force and the time, which we call the impulse. Okay. So impulse, or force times time, is equal to change in momentum. So we have two possible units for impulse, one being force times time, so Newton seconds, and the other one being change in momentum, momentum being mass times velocity, so kilograms meter per second. Impulse, like momentum, like velocity, is a vector quantity. So you need to consider directions when doing that. And our usual way of doing that is to make one direction positive and one direction negative. Sometimes we might see the relationship written as the bottom here, where P is equal to momentum. So delta P, delta means the change in, so the change in momentum is equal to the force times the time. Okay, so the change in momentum of any object is the difference in the momentum from its initial speed to its final speed. And this and the impulse are equal to each other and so have the same units. So you can show the change in momentum in Newton seconds, or you can show the change in momentum in kilogram meters per second. Both are the same. So let's look at a problem here. So a force of 100 newtons is applied to a snooker ball that has a mass of 150 grams for a contact time of 0.020 seconds. And we're asked to calculate the final velocity of the ball. So the unbalanced force is going to cause the ball to accelerate. We want to know what it's going to accelerate to. So looking at the relationship here, the impulse Ft is equal to mv minus mu, and then we substitute in our values here, taking care to change the mass into kilograms and the time, making sure the time's in seconds. Sometimes the times can be in milliseconds because the contact times can be quite small. and this gives us a velocity of the snooker ball at the end of 13.3 meters per second. Let's look at another example here. So this time we're hitting a golf ball, 50 grams mass, off the tee at 30 meters per second. And there's a contact time between the club and the ball of 25 milliseconds. And we want to know what the average force is going to be exerted on the ball. So impulse, Ft, is equal to change in momentum, mv minus mu. So F times the time in milliseconds, so we've got 25 times 10 to the minus 3 here, is equal to 0.05, because that's the mass in kilograms, multiplied by the 30, take away the initial velocity of the golf ball, which was on the tee, which will be 0. And so that gives us a force of 60 newtons. Okay, it's possible to do an experiment in class to show this. Sometimes it's done with a ball and a cue, like here. Sometimes it's done with a golf club and a ball as well. And what we've got in the diagram is we've got two bits of apparatus. So we've got one bit of apparatus on the left there that's going to measure the contact time of the cue in this case, and the ball, or the club and the ball, depending on what situation we've got. And the second one on the right there is to measure the velocity of the ball, so we can know what the final speed of the ball is, or the time to go through the timer is, and then work out the final speed at that particular point. So timer 1 is going to measure the contact time with the ball. Because the cue in this case, or the golf club, is made of metal, and the track and the ball are also made out of metal, when the cue hits the ball, this completes the circuit, and the circuit is completed as long as the ball is stationary. When the ball starts to move, the circuit is broken, and so you get the contact time from how long this circuit is completed for. The ball then moves along and goes through the light gate. By dividing the diameter of the ball by the time on the timer, we can get a final velocity. And then if we have the mass of the ball, by putting it on a mass balance, and we measure the diameter of the ball, we can then work out the average force of the ball. Okay, so this is all taking place by completing an electrical circuit to measure the time of contact. That's the harder part to do. So the ball itself would be covered in something like tin foil so that it conducts rather than looking like a normal ball. Okay, we're going to see a video of this experiment taking place. Okay, so the ball is hit with the metal cue. It measures the time of contact, measures the time for the beam to cut there. Our initial velocity is 0. And we can work out our final velocity using the diameter of the ball divided by the time to cut the light beam, and then we can work out our force from our impulses change in momentum relationship.
Oh, okay troops, another exciting higher physics experiment here. Today we're going to try and calculate the average force that we exert on a ball when we hit it with a cue. And we're going to try and do that by measuring the change in momentum of the ball. Its initial momentum is 0, and then we're going to measure its velocity when it goes through the light gate using a TSA. We're going to measure its mass, and we're going to measure the time of contact between the metal cue and the metal ball on the metal track by having the cue and the ball and the track all connected into a circuit where we can measure that time of contact just by tapping the ball. So we have to set this up to measure a very fast time. Okay, ready to go. It's waiting. Next, we're going to use this TSA computer to measure the speed of the ball. So let's set that up. Measure speed. Now, make one measurement of speed. 1. The mask size is the diameter of the ball. That's a 4 centimeter ball. So let's put in centimetres. And we're ready to go. So a 4 centimetre object going through that light gate will allow that TSA to work out the speed that it's going at. The only other piece of information we need is the mass of the ball. Right? There's the mass of the ball. So put the ball very close to the light gate so that we minimise the effects of friction slowing the ball down once it's been hit. Remember, the law of conservation of momentum states that the total momentum before equals the total momentum after in the absence of any external forces. So let's go. That one's waiting. That one's waiting. We're going to measure the time of contact and the velocity of the ball. Here we go. Metal cue, metal ball, light gate. There's our results. Time of contact, 1.3 milliseconds. Speed, 0.49 meters per second. Let's see how we got on.
Okay, so let's take those results and work out what we've got there. So we've got the time of contact, the mass of the ball, and I've written down here the time to pass through the light gate because sometimes you get given the time. I could see on the video that we're given the velocity and the diameter of the ball. And we're asked to work out the average force. Okay, so the first thing that you might need to do is to work out the final velocity, which would be the diameter of the ball going through the timer, okay, which gives us our 0.949 meters per second. So that was displayed on the TSA box, but you saw that you had to put in the 5 centimeters diameter and the time would have been measured from what took place there. Okay, we then substitute in our other numbers. So the force times the time of contact, 1.36 milliseconds. So times 10 to the minus 3 there is our mass of the ball in kilograms. So it was about 21 grams. We've just rounded that up. And we've put that in kilograms multiplied by our 0.49 minus 0 because its initial velocity was 0. And that gives us a force of 7.6 newtons. So in our video here, we've talked about the law of conservation of momentum again, and that impulse is the quantity that is the force times the time or the change in momentum, and has two possible units, newtons per second or kilograms meters per second. And we've looked at how to carry out calculations using this.